were even in existence when the questions were stated. So there's mathematics. Now let's talk about computers. So there's the first ever computer programmer, Ada, Countess of Lovelace. So why is she the first ever computer programmer? Because she wrote the first ever computer program. So a guy called Charles Babbage, he was not really a mathematician, he was more an engineer, but he designed something called Babbage's analytical engine. And the idea, you know, it was a machine, but actually it was a machine where you could set the dials and you could actually tell the machine to do lots of different things. It was a very primitive kind of computer. You set the dials, that's like writing a program, and then you run the machine, and the machine runs according to where the dials are set. So this is really the first computer that was around in some sense, this analytical engine. And Babbage gave lectures on it in Italy, somebody took notes in French, and these notes made it into the hands of Ada Lovelace, who decided she'd translate them to English. And while she was translating them, of course you translate something, you read it, she read it, she learned the material, and then she wrote a series of appendices at the end of Babbage's notes. And Appendix G, the last appendix, is an example of where you could set the dials in order to run a program that would compute Bernoulli numbers, which were at the time were a thing. Like, you know, people would compute things by sitting down with pieces of paper and writing them all out. And her observation is Bernoulli numbers kind of a bit annoying to compute. But if we have one of these analytical engines, then actually we could just set dials like this, switch it on, and out come the Bernoulli numbers. It would, you know, save somebody a job. So Ada Lovelace, she wrote the first computer program, and so we can ascribe to her a theorem: a computer can calculate Bernoulli numbers, right? And the proof is, do it. Just like the proof of bisecting the angle was doing it, the proof is, let's just write a computer program that computes Bernoulli numbers. So that's what she did. She never saw it run, because Babbage's analytical engine was never built. In fact, they had there were technical design problems at the beginning, and by the time these things were resolved, the money had run out, the funding dried up, and the analytical engine never got built, and Lovelace died at 36, and never saw her program run. But of course, nerds went away and, you know, made other ones, so it does work. And it computes Bernoulli numbers. So you can see, if you're thinking, you see where the story's going, right? So now we skip forward 100 years to Alan Turing, and Alan Turing, he thought about computers as well, but he wasn't an engineer, he was a mathematician. And so he started thinking about mathematically modelling a computer, kind of like using arithmetic to study points in geometry. He started to wonder whether you could kind of model a computer using the language of mathematics. And nowadays this thing is called a Turing machine. And Turing's mathematical description of a computer, it opened the doors for mathematicians now to start proving much more deeper and profound results about what computers could or couldn't do. And of course we're in just the same situation, right? You've got a problem, the question is, can a computer do it? If the answer is yes, how do you show the answer is yes? You just write a computer program that does it. How do you show the answer is no? It's going to be difficult, right? So Lovelace isolated this interesting problem, computing Bernoulli numbers, and showed a computer could do it. And Turing also isolated an interesting abstract problem, but he showed, because he had more tools than Lovelace, he showed a computer could not solve this problem. And again, when you just step back, however are you going to prove something like that? How can you check that every single computer program that ever was written, will be written, can be written, will not solve this problem? I'm going to try and explain to you how he did it. And the problem, it wasn't just an abstract problem as well. It's not just this bisect the angle nonsense. This is kind of sad thing. Banzel proved you couldn't trisect the angle. By this stage, nobody cared. Whereas Turing worked on a problem that actually, even though in 1936 when he worked on it, there were still no computers, right? The first computers started appearing in the 40s. And you know, Turing actually was involved in several of them. But Turing proved this theorem in 1936 before a single computer had ever been built and a single computer program had ever been run. And he proved, and he was interested in the idea that computers might sometimes crash. And computers crashing is a pain, right? You lose data, you lose information, you have to switch it off and on again. We don't want computers crashing. Turing could see that this was going to be an issue before any computers ever even existed. So, I'm going to try and tell you a bit about what Turing did. So let me try and explain to you what a computer program looks like. So this is a computer program written in pseudocode. So it's kind of written in English, but there's lots and lots of steps. And what the processor will do is it will just go from each step to the next step unless somebody tells it to do something else. And at each step it will carefully read what's there and it will do what it's told. Okay? And it will do it very, very quickly. So this computer program here, step 1 is going to ask the user to start. So you run it, you click on, you have it on your phone, you click on the little app, and a little screen pops up, says type in a number. And then you type in a number like 53, and you click OK, and you've typed in 53, and the box disappears. And now step 2 is let X be that number. So now, if we type in 53, X will be 53. Now step 3 is a funny thing that involves the question, is X equal to 7? But we've typed in 53, so X isn't equal to 7. If X was equal to 7, we would have gone somewhere. So X isn't equal to 7, so we go to step 6. So we've typed in 53, X is 53, we're at step 3, X isn't 7. So let's go to step 6. Step 6, print hello on the screen and then we stop. So when you run this app on your phone, you click on the little app, it says type in a number, we type in 53, we click OK, another little box pops up saying hello, and then that's it. That's finished. So, and that's if you play with it for a bit, you'll realise that that's what it normally does. But then eventually, you hit on the idea of typing in the number 7, and so you type in number 7, the computer lets X be 7 in step 2. In step 3, it notices that X is equal to 7, and so instead of going to step 6, it goes to step 4. And in step 4, it has to see what to do. Step 4 says go to step 5, so it goes to step 5. And step 5 says go to step 4, and so it goes to step 4. And then step 4 says go to step 5, so it goes to step 5. And it just alternates between step 4 and 5. And this is what you can tell the computer's not thinking. Because if a human had to do that, they'd get bored at some point. But the computer will just keep doing it. That's exactly what they're paid to do. They just quite happily, mindlessly follow the instructions. So the computer will get stuck going between steps 4 and steps 5. Now you're running this, if your operating system gets stuck in that kind of loop, then it stops. You see line 1 is kind of implicitly saying, what's the person pressing on the keyboard? But if you're just hopping between step 4 and step 5, the computer isn't looking at the keyboard or the mouse or anything like that, and you wiggle these things around and nothing happens, and you know what's happened, right? When your computer's in that state, you press the caps lock key and the light doesn't come on, you know that your computer's had it, and you have to switch it on and off. So computer programs sometimes get stuck in loops, and you've all seen it happen. So there you go. If the user types in the number 7, that computer program gets stuck in the end of this loop, so it crashes, right? So here's a much more complicated program, and we're not going to analyse it because we just basically spend all day analysing it. All I'm showing, that other one had 7 steps, this one's got 9 steps, but it's vastly complicated. You ask the user to type in a number, let's say they type in the number 9. Step 2, let X be that number. Step 3, X is 9. If X is bigger than 10, it's not bigger than 10, 9 is less than 10, so we go to step 6. Step 6 says if it's less than 10, and it is less than 10 because 9 is less than 10, so we go to step 4. Step 4, X changes. Step 4, we replace X by 2 times X, so now suddenly X was 9, so now it's 18. And then what do we do? Then we go back to step 3, now X is 18, and now X is bigger than 10, so we go to step 7. And you can see we're kind of jumping around, right? But X is 18, step 7 says if X is less than 100, go to step 4. Step 4, we've been to step 4 before. So you kind of think, oh, we're in an infinite loop, but we're not in an infinite loop, because when we were at step 4 before, X was 9, and now we're at step 4 again, but X is 18. And so we're not in exactly the same state as before, so we might not be in an infinite loop. And X is going to be replaced by 36, and you can kind of see it jumps around, right? And we didn't even go to, there's like some, step 5 is ridiculous. It's not really clear whether this is the question, can this computer program get stuck in an infinite loop? That is a tricky logic puzzle, right? And I don't fancy doing it. Somehow I would try and do it using intuition. I would kind of try to find key numbers which somehow behave differently to other numbers. But can this computer program get stuck in an infinite loop? Figuring out that kind of question is a complicated logic puzzle. Now, I like doing complicated logic puzzles, but actually, at the end of the day, what kind of gadget is really suited to solving complicated logic problems? It's a computer. So what we should really do is not bother solving that problem at all. We should, what does that mean? That doesn't mean I stop, right? I'm halfway. Oh, that's good, because I'm halfway through the slides as well, because the last 2 slides are jokes. So this is the sort of puzzle which would be ideal for a computer to work on. And so, this is what Turing decided to work on. Let's write a computer program that checks other computer programs to see if they get stuck in infinite loops, right? So when a computer program gets stuck in an infinite loop, well, it's crashed, and that's bad, right? So we'll say a computer program is bad if it can get stuck in an infinite loop, and we'll say a computer program is good if it never gets stuck in an infinite loop, right? So there's some definitions And now Turing says, how do we check to see if a computer program is good, right? We want to tell the good programs from the bad programs. So he's going to write a computer program, right? So in his 1936 paper, he abstractly axiomatized mathematically what a computer was, and so now he could use mathematics to work on this question, and he found a solution, which, as I say, you probably guessed. So Turing's going to try and write a computer program, and the input to the computer program is not a number, and this isn't about, like, you've probably gone to some website, and I do this when I'm typing in, when I'm writing references. You click on something, it says, upload your reference, and you find the reference and you just drag it over. It's not. Computer programs will quite happily accept random files as inputs rather than just numbers. So this computer program that Turing's going to write, is going to write a computer program that takes as input an arbitrary computer program, a different computer program, and then Turing's computer program is going to print out good if it's a good one and bad if it's a bad one. Okay? So Turing's going to try and design that computer program. Okay? So, but actually, something interesting has kind of happened here, because if I've got a computer program that takes as input a computer program, that means that you kind of like take the computer program itself and kind of put the computer program into itself, which is a little bit meta. And that was somehow, that was where the fun started. So Turing realised if he could tell good from bad with a computer program, then he could write a ridiculous, useless computer program K, which would behave like a bad program if you inputted a good program, and would behave like a good program if you inputted a bad one. So the idea is you input the program, the computer program, crazy program K figures out if it's good or bad. If it's bad, that's great. It just, if it's bad, it will just stop. And if it's good, it will intentionally go into an infinite loop and be bad. So program K is bad if the input's good, and program K is good if the input's bad. And then, of course, you take program K and you feed it into itself. Okay, and now what's the consequence? So now we could ask, is the answer going to be good or bad? If K is bad, then you feed it into K, and it is good, right? If K is bad, then K must be good. And if K is good, then K must be bad. So there's something wrong, right? Because a computer program can't be both good or bad. So we must have made a mistake, because we've got a contradiction. And the mistake is, of course, the two-letter word that I underlined, that I put in red, right? The mistake is Turing's initial assumption that we could write a computer program which can tell good code from bad code. So that's Turing's mistake. I mean, it's not a mistake if it's an assumption. The assumption is the only part of the argument that he could make completely logically valid, so his assumption is wrong. And Turing's conclusion is that it's impossible to write a computer program which can check any and every other computer program for bugs. You cannot, and this is why computer programs still crash, because it's impossible to check that they've got bugs. So Turing rigorously proved that in 1936. Remark, still before any computers had existed. Took him. I mean, I sketched the idea, but what I want to stress is absolutely crucial to it all was the fact that he could he'd abstracted what a computer was and put it in mathematics. So there we go. So there's a summary of this bit. Lovelace proved that a certain interesting problem can be solved using a computer program. The proof was just do it. Turing proved that a certain problem could not be solved using a computer program 100 years later, once the machinery got more sophisticated. So again, we see an example. Turing proved that it was impossible to do something. And in my mind, that's kind of an amazing thing to prove you can't do something. Okay, so it's formally just like trisecting angles, right? So this is what happens in life, this is what happens in mathematics. People work on areas of interest, and eventually they run into obstructions, they run into problems which they can't solve, and people work on them, and of course sometimes they get solved later on, but sometimes they remain obstinate, and then eventually it turns out the reason they remain obstinate is because the answer is that your mathematical machinery cannot solve this problem. Right. So very brief summary. We can prove it's possible to do something by doing it. We can prove it's impossible to do something, but it often lies doing that. So we've seen an example in pure mathematics, and we've seen an example in theoretical computer science. Theoretical computer science with a capital T, really, because what do I mean? There's an issue with Turing's computers that I'll come to now. So what we're really interested in nowadays is because now computers do exist and they're becoming vastly dominant in our lives, I'm going to talk about a practical problem involving computers. So let me first tell you, I told you that Turing axiomatized abstractly what a computer was, and here's some of the problems with Turing's theoretical notion of a computer. Firstly, had an infinite amount of memory, because mathematicians are kind of used to things being infinite. There's infinitely many numbers. So had an infinite amount of memory, and he didn't really care about processing speed. All he cared about was, did it get stuck in an infinite loop or not, right? So if you had a program that it turned out got stuck in a loop that would basically take 1 million years to get out of, but in 1 million years your mouse will magically start working again, and your computer didn't crash after all. You see, you don't really, you don't somehow, if it's going to take 1 million years, you're not really interested. Right? So in reality, computers have memory, and memory, this is an engineering question, memory is made out of stuff, right? Like terabyte hard drives are made out of tiny, tiny little magnets, and solid state drives are made out of tiny little, electrical circuits. But any memory location that stores a piece of information is going to needs to be physically made if we're going to make one in our universe and stop looking at abstract computers like Turing. So we're going to need at least a particle, okay? At least, bare minimum, we're going to need a particle to make that thing. And unfortunately, there's only 10 to the power 80, but that's 1 with 80 zeros. There's only 1 with 80 zeros, there's only that number of particles in the entire universe. So that puts a limit on how much memory actually a computer can have. And similarly, quantum mechanics says that when you look very, very small, things get much weirder than you might expect. So one of the consequences of quantum mechanics, some currently believed theory, is that there's basically a smallest unit of distance which is meaningful to talk about. And beyond that, things just kind of get too straight. And it's a very tiny distance, but beyond that distance, somehow everything becomes meaningless. Now, information, if you believe relativity, information can't travel faster than the speed of light. So one might ask, how long light would take to travel one of these Planck distances. It's all to do with Planck's constants. And it turns out that light would take 10 to the power minus 44, so that's 0 point and then 44 noughts and a 1. No, it's not. It's 0 point and then 43 noughts and a 1. There's 1 Planck time. 10 to the minus 44 seconds. So you cannot hope that your computer can do anything, because it's impossible to do anything in a unit of time shorter than 1 Planck time. Where, of course, the Earth will become uninhabitable around 1 billion years. If we're interested in computers on Earth, then this is going to be an issue. And if more generally we'd be interested in kind of computers in the universe, then we have to kind of figure out when the heat death of the universe will be. But I read a lot about this on Wikipedia, and it's somehow that scientists aren't sure. They don't really know if the universe is going to expand forever. I mean, they believe in the Big Bang, but they don't know if there's going to be a big crash or if it's just going to stop. So I don't really know when the universe will end, but certainly the sun will burn out in a few billion years, and by 1 billion years there'll be this red dwarf, and the seas will be boiling. And again, if you think about it, that puts some theoretical limit on the number of instructions that any computer can do. So let me just summarize. So to summarize, I'm not now interested in Turing's abstract theoretical computers. What about computers on this planet? They can't run a program which involves storing that much information, where that much is just some number I've chosen, very large, to make sure that it's more than the number of particles in the universe. And similarly, they can't run computer programs in which the processor has to do that many instructions, because again, I've just chosen this very, very large number to make sure that even if it did 10 to the power 44 instructions every second, it's still, the world is going to be a dead hulk by then. So these are limitations that Turing didn't have. Turing didn't really care. I mean, Turing had other things to think about. There was a war on, and when these issues are now practical, right? It's not just can we solve the problem or not. It's can we solve the problem quickly? Okay. So these now give rise to new questions. This is the last thing I'm going to talk about. The remainder of the talk, I'm going to talk about a third question. So here's two computer, they're not like these nightmare ones that I just showed you. Here's two very simple computer programs, because I need to teach you the concept. Computer program 1, the user types in a number, the user types in 53, and then step 2, let x be that number, so x is 53, and all it does, it doesn't print hello this one, it prints out x, okay? So sample run of program 1, the user types in number 53, and clicks OK, and the computer prints out 53. So it just prints out what you type. Okay? So computer program 2 formally looks very similar. This time, the user types in a number, you let x be that number, but now instead of printing out x using our normal notation for printing numbers out, instead all it does is print out x things. 53 has a meaning, right? 53 means 53 things. So actually, instead of printing out our clever notation, it actually prints out the meaning of the number. So it prints out 53 things. So, well, I mean, if you don't like line 3, then how do you actually print out x zeros? What you would really do is you would just print out 1 0. and then you'll decrease x by 1. And if it was still positive, then you'll keep going back. So you'd actually do this using a loop. So that's how you print out x zeros using a computer program. So now, of course, sample run, let's type in 53 again, and this is the output. We just get 53 zeros. So now let's have a race, program 1 against program 2. We'll type in 53 to both of them, and who's going to win? Program 1's going to win, because program 2's got to do a lot more work, you see. First program's going to finish, I mean, in practice, of course, both will finish in the blink of an eye, so you won't even be able to notice. But I want to explain a way of telling why this second program must be worse than the first program, why it's sort of less, why it works more slowly, and it's because of scaling. So by scaling, I mean, let's not type in 53, let's now think about typing in a bigger number, let's type a 5 and then a 3, and let's type another number. So instead of typing in 53, let's type in 531. Okay, and now let's run our two programs. We saw what happened when we typed in 53. Now let's type in 531, right? And the first program, well, it used to have to print out 53. Now it's going to print out 531. It just takes one more digit, right? Not very much more time at all. The second program is going to print out 531 things now, and 531 is about 10 times 53. So the second program is going to take 10 times as long to finish. So they behave in very different ways with a small perturbation of the input data. If I make the input data a little bit bigger, the first program deals with it easily. The second program, the amount of time it takes gets multiplied by a constant, so you have this compound interest phenomenon. Like if you leave a penny in a bank long enough, eventually you'll get to £1 million, because things can blow up sort of substantially. If you double your money every time, then by the time you've doubled your money 10 times, you've multiplied your money by over 1,000. So this is an issue that the second program has. It doesn't scale well. You make the input a little bit bigger, and suddenly it takes a lot longer to run. So when you're trying to solve real-world problems, the input data might well slowly increase. So you want to make sure that your computer program doesn't ground to a halt if the input data starts getting bigger. So an example is, it's a very complicated problem trying to work out when all the students in the college are going to take exams. Because lots and lots of students are registered for lots and lots of different courses, so you have to make sure that every student, they haven't taken 2 courses for which the exams are at the same time, but all the exams are going to be crammed in to a small period of time, so you have to have some exams at the same time. It's a very delicate question. So right, if we wanted a computer program to solve, and of course we do have a computer program to solve this, then we want to make it scale like program 1, not like program 2. So scaling, I talked about it informally, but mathematicians have formalised these notions. Okay. So the first time you do a historical search, the first time you see this notion of really beginning to care about not just abstractly whether computers can do things, but how long it takes them to do them. The letter, 1955 letter from John, this is the Beautiful Mind guy, 1955 letter from John Nash to the NSA, the American security agency, where he began to lay down, he isolated the issue that actually it's not about whether the computer can solve it, it's about how quickly the computer can solve it. And he raised explicit problems in the area, some of which he can solve. So, if you like, so I'll tell you what Nash said, because these are kind of important words, and this is just, so a computer runs in polynomial time if it scales like the first program. That's an informal definition. I'll give you a proper definition. Here's the proper definition. There. So formally, a computer program runs in polynomial time if there's a polynomial function, like that, n to the power 20 plus 1,000, such that if you input a number with n digits, then the computer program will churn away and it will finish. But how long will it take to finish? The program will finish, but it will do at most p of n steps. Okay, that's the idea. If you can write a computer program like that, then you've got a polynomial that's kind of controlling how fast your computer will take to calculate. And polynomials don't grow too quickly. This is somehow morally the thought, but also in practice, polynomial-type computer programs are what people are after. If you've got a problem you can solve in polynomial time, then somebody has already written the code that will solve that problem for you, and it will run very efficiently. So we're interested now in the collection of problems which can be solved. We can be solved with a computer, and furthermore, the computer can solve it quickly. Problems that can be solved in polynomial time. And mathematicians, being what they are, they needed a name for this collection of problems, so they called it P, because that's what they do. So that's now called P. It's a collection of problems which we can solve in practice quickly. Okay. So now let me just mention code a little bit. Secret codes are really good. You agree on a secret code with your friend, and then you've got the secret code, your friend's got the secret code, but nobody else has, and now you can send messages to your friend using the secret code, because you've got your message and you encrypt it using the secret code, you send it to your friend, and they decrypt it using the secret code. You've both got the secret code, but no one else has got the secret code, so it works. So I'm afraid nowadays, things aren't so easy, because I want my phone to kind of connect to random... I want my computer to talk to other... If I go to a website I've never been to before, my computer is suddenly talking to another computer that's never met before. And I might have to type in my credit card details if I want to buy something. And now I need to talk to this other computer. I need to send the computer a secret piece of information. But we haven't got a secret code. And how are we going to... You see, the problem is people can hear what you're doing on the internet. Your ISP knows what you're doing. You know, the government probably knows what you're doing. And like people that are just generally snooping around on the internet might see packets going by through your computer. So this is kind of a problem, and it means secret codes aren't good enough anymore. We need something called public key cryptography, where the idea is I establish a code we're going to use, and even if somebody is snooping on my packets, even if my next door neighbour has got some kind of Wi-Fi detector thing, and they're watching all my Wi-Fi packets, I need to make sure that they can't find out what my credit card is. So these things are called public key codes, public key cryptography, and rather surprisingly, they exist. They were invented in the 70s when it was realised that these things were important. And the way they work is they exploit asymmetries in encoding and decoding algorithms. So the idea is you want to make sure that encoding is quick, but decoding is slow. So let me give you an example of an asymmetry. We've got a piece of cotton. I'll give you a long piece of cotton, and I'll give you 2 minutes, and you can tie as many knots in as you like. And you can tie lots and lots of knots, and at the end of it, you can imagine you can make this piece of cotton into a real mess. Lots and lots of tiny little knots. You pull them tight, but like after a while, the knots kind of get. You've ever done this? I've done this. The knots kind of get closer and closer together, and they kind of start compiling up on each other. And at the end, you get a nice kind of chunky little thing that's really difficult to untie. So you turn a piece of cotton into a big complicated knot. It's very easy. Give me a couple of minutes, I'll give you a complicated knot. On the other hand, you've got a big complicated knot, you've got to untie it, it's going to be very difficult. See, it's going to be possible, but it's going to take a lot more than 2 minutes. Okay, so some things in life are asymmetric, right? And surprisingly, something that you know a lot about, multiplication, turns out to be one of those things. So here's a multiplication problem. We don't have to do it. I'm going to tell you the answer, don't worry. What's 43 times 61? There's a method, right? You learned it. It's called long multiplication. 43 times 61. There we go. We do 1 3, we do 1 4. 3 6s and 4 6s. And then we do some adding and we've got the answer. And how many steps did we actually take? We did 1 times 3, 1 times 4, 3 times 6, 4 times 6. We did under 10 steps. Okay? So long multiplication is actually a really good method for multiplying numbers together. That scales very well. Here's the clue that it scales very well. What are the numbers involved? The smallest number involved is 43. But did it take 43 steps? Right? Did we actually, remember that computer program that you typed in 43 would print out 43 zeros? That takes 43 steps. Here, we didn't use anywhere near 43 steps. We did it in under 10. So that's the clue, it scales very well. Okay? So now, let's unmultiply. So here's the answer, 2,183. I timed 2 numbers together, and I got 2,183. And what were those 2 numbers? Now, they don't teach you how to do that at school. And so let's do trial and error. Was it 2 times something? We could divide 2,183 by 2. It doesn't work, we get remainder 1. So let's divide it by 3. It doesn't work, we get remainder 2. And so it's divided by 4, or if you're smart, you'll skip 4 because you've done 2 and you'll go to 5. But you keep dividing and dividing and dividing, and eventually you divide it by 36, it doesn't work, you get remainder 23.
One of our coffee, hosting the
Gets scheduled optimally, we save lots of fuel, people and goods move around quickly. Factories become infinitely more efficient, dramatic advances in medicine, because suddenly we can cure cancer. I don't think cure cancer, we can certainly do much quicker experiments. Perfect computer vision, computer language recognition. So, you see the problem, it wasn't very important in 1971, but better predictions of weather and of earthquakes, huge advances in modern mathematics, because solving a mathematical problem is a great example of something that's in NP. I work on a problem, I can't do it, there's lots of axioms, I don't know how to apply them or what orders to apply them in, but if somebody comes along and hands me a proof of this, if someone says, I can prove the thing, I can sort out the thing you're working on, here's the question you're working on, here's the proof of it, I can read the proof really quickly, I can check that that's a mathematical proof, that's kind of part of my training. So I can check the answer quickly, and so if P equals MP, I can solve the problem quickly, so we can just get computers to do lots and lots of modern mathematics. It also means, of course, that there's no such thing as encryption anymore, so the government can read all your emails, even if you encrypt them, and internet security is now broken, you can't type your credit card into the internet, so online banks instantly, everything gets stopped. So society really changes. The internet stops working, but maybe we can cure cancer. So but the world will be a very different place. Unfortunately, or possibly fortunately, most computer scientists believe that P is not equal to MP. They believe that there are problems out there which are easy to check but hard to solve. Easy to check the solutions but hard to solve. So what would happen if we proved that P was not equal to MP? Then we know we have algorithms which we now guaranteed can't be solved quickly. Now we definitely know we can talk in code. So I know that the government can't spy on me. That's really good. And terrorists also know that the government can't spy on them. And all the people that are currently selling illegal drugs and weapons on the dark internet, and that really is happening, they can sit comfortably knowing full well that they can definitely not be traced. So again, the world changes a little bit, and this is currently the working model, right? Theresa May was very, very upset about this. There was an iPhone story, you remember this? Some guy, there was incriminating evidence on his iPhone, but they couldn't unlock it, and Apple said they weren't going to unlock it. And the problem resolved itself, but that's the tip of the iceberg. More will happen again. There will be police officers that know full well that there's an encrypted drive that if they can decrypt, then this guy is nailed, but they can't decrypt it. If P is an MP, we can design codes that are going to be impossible to break. So it should be clear that it's clearly important to work out if P is MP or not, right? So all the problems in P are in MP, but the question is, are there problems in MP but not in P? to me. I thought I'd finished. If you tell me the solution to a problem in class B, I've said all this already. So how? No, this is the point. Sorry, I'm going to tell you the point. How is a mathematician? So P probably isn't equal to MP. So how's a mathematician going to prove that? Right. And this is the point. All they have to do